Hi, I am Allison.
I'm Uli.
And I'm Ankita.
Thank you for joining us for What a State We're In, our contribution to the Northern Ireland Science Festival 2021.
With our friends from Bristol Free School, we're going to take a tour through some of the states in which matter can normally be found and take a peek into how some more unusual states can be created in particle accelerators.
Along the way, we have several science at home practicals you can try yourselves.
If you do have a go, make sure you have an adult's permission. It is their responsibility to make sure you work safely.
Without further ado, it's over to Maya, who's going to kick things off with an introductory segment on the states of matter which we encounter most often.
In this talk, we will be discussing about different states of matter. For many of you, this will be a recap, but it sets the stage for some of our demonstrations later. We are going to look at the 4 distinct forms of matter that we commonly see: solid, liquid, gas, and plasma.
Firstly, let's talk about solids. In a solid, particles are packed closely together, giving it a high density. Atoms vibrate around a fixed-in position, but don't move freely. Particles in a solid have a very low kinetic energy relative to the other states. Solids have a definite shape and volume, and many solids have long-range order. Solids have the lowest entropy out of all the states of matter.
Entropy is a measure of the possible number of arrangements for a system's particles. It can also be thought of as a measure of the amount of disorder in a system. When a solid changes state into a liquid, we call it melting. As a solid is heated, its particles gain kinetic energy, eventually moving fast enough to break the physical bonds between them and allowing them to flow and move around each other. You can easily show that it takes energy to break bonds in a solid. When a solid melts, the energy needed to break bonds comes from its surroundings. You need to warm it above its melting point.
If you dissolve a solid in room temperature water, there isn't an obvious source of energy. However, if you observe the process with a thermal camera, you can see that the temperature of the liquid falls during dissolving. Energy cannot be created or destroyed, so thermal energy in the water is being converted into potential energy as physical bonds break. This process is driven by an increase in entropy. By dissolving the solid, you create more possible arrangements of particles. State changes for pure substances take place under specific conditions. For example, the melting point of water is 0 degrees Celsius at a pressure of 101 kilopascals.
However, mixtures like chocolate melt over a range of temperatures. Chocolate is a colloid, which is one substance dispersed through a second substance. Solids can change into a gas without passing through the liquid state. This is called sublimation, and the reverse process is called vapor deposition. Vapor deposition is a process that can make extremely pure layers of substances, such as silicon, used in the manufacturing of computer chips and pyrolytic graphite, which we use for a trick or two. Sublimation happens at temperatures and pressures below a substance's triple point, which we will cover a little bit later.
In a liquid, molecules are still relatively close together and can flow over each other, giving the liquid an indefinite form. Because they do not take a definite form, liquids take the shape of their container. There is little space between each particle, meaning that liquids are pretty much incompressible. So, liquids are said to have a definite volume, but no fixed shape.
In comparison to solids, particles in a liquid have more kinetic energy and a higher entropy. Because their particles are not stuck in a fixed position, there are many more ways to arrange them. Freezing is when a liquid changes state into a solid. It happens when the particles lose enough kinetic energy to stick together. As the temperature of the liquid reduces, heat flows into the environment until the particles no longer have enough energy to remain free from each other.
When a liquid changes into a gas, it is called boiling. The kinetic energy of the particles increases as the temperature increases. When a molecule near the surface absorbs enough energy, it will escape. Temperature is a measure of the average kinetic energy of a substance's particles. Because the particles in a liquid have a range of energies, the fastest moving might have enough energy to escape, and we call this evaporation. Evaporation lowers the average kinetic energy of the particles in a liquid so evaporation cools liquids.
Making new surfaces takes energy, which means it's difficult for one state to push its way out of another. For example, bubbles or ice crystals forming. So although state changes should happen at the same temperature each time when the pressure is kept constant, this doesn't always happen. For example, if you put pure water into a freezer, it doesn't freeze until it reaches around -2 degrees Celsius, and then it freezes very quickly, which is why you see rushes of bubbles fossilized in ice cubes. Taking the water out and shaking it causes lots of ice crystals to form. We'll investigate something similar a bit later.
In a gas, the particles are spread out randomly and have a large amount of kinetic energy. The particles are much further apart than in solids or liquids. Gases have no definite shape or volume due to the random order and motion of their particles. This means that gases have the highest entropy as, for a given amount of substance, they have the largest number of arrangements possible.
A gas will expand to fill its container. When a gas is put under pressure by reducing the volume of the container, the space between the particles is reduced, and we say that the gas is compressed. Temperature, pressure, amount, and the volume of a gas are all dependent on each other. As temperature decreases, the particles in a gas lose kinetic energy, and when below the condensation point, the gas will condense back into a liquid.
Here we have some liquid nitrogen. It boils at -196 degrees Celsius at normal atmospheric pressure. If we pop a little bit in here, you can see that it boils vigorously. Heat energy flows from where there's a lot to where there's less. So heat flows in from the surroundings, providing the energy needed for nitrogen molecules to escape the liquid. You can see that the resulting gas takes up much more space. Most of the cooling effect of liquid nitrogen comes from it boiling. The change of state absorbs around 200 times as much energy per molecule as raising its temperature by 1 degree Celsius. We're going to come back to the cooling effects of nitrogen a bit later.
Finally, there's plasma, probably the least familiar state of matter, and is the highest energy state that we encounter on Earth. Plasma is the most abundant state of matter in the universe. Some of the best examples are stars, which are basically superheated balls of plasma. On Earth, you find plasma in a variety of places, such as fluorescent light bulbs and lightning.
Flames also contain plasma. The orange region is mainly hot atoms, but the blue region is plasma. Plasma consists of highly charged particles with huge amounts of kinetic energy, which move freely, like those in a gas. Plasma is different from gas, because it is made up of positively charged ions and negatively charged electrons. It can be affected by electric and magnetic fields. Ionization is the process by which atoms and molecules acquire a positive or negative charge by either gaining or losing electrons. The opposite of that is known as recombination. The blue light given out by hot flames is where ions recombine with electrons, and the sharp color difference between the orange and blue regions is where the temperature transitions below being hot enough for plasma to exist.
So I hope you enjoy learning about different states of matter. Now you can look forward to naming different ones you see every day.
And now it's over to Tabitha for our first Science at Home practical, which is all about liquids, gases and solubility.
Hello everyone, I'm Tabitha, and welcome to our first Science at Home practical. This is one you can do yourselves, but do get permission first. We are going to be doing the classic Coke and Mentos experiment. For this practical, you do not need a lot of equipment, just a bottle of Diet Coke and a few Mento mints from a fresh packet. If you use a 2-litre bottle, you'll need roughly 6 mints, and if you use a 500ml bottle, you will only need 2 or 3. Regular Coke will work too, but one of the artificial sweeteners in the diet version helps to form bubbles by lowering the liquid's surface tension, so Diet Coke is best. Chemicals that do this are called surfactants, and an example would be washing up liquid. If you are going to try this demonstration, make sure that you are outdoors as it can be quite messy. Place the Coke bottle on a level surface and make sure that it is stable. Remove the cap from the bottle and carefully add several Mentos. We added 6 as we are using a 2-litre bottle. It's probably a good idea to jump back at this point, but be careful you don't knock the bottle over.
Yep. Well, that's wow.
If you want, you can repeat this experiment in several different ways, varying the number of mints and the type of carbonated drink to see how the size of the eruption changes. But what exactly is happening here? Firstly, where do the bubbles come from? To answer this, we need to ask, what makes fizzy drinks fizzy? All fizzy drinks have carbon dioxide dissolved in them, but the gas is dissolved at a pressure around 3 times higher than the atmospheric pressure. This allows much more of the carbon dioxide to dissolve, and then the bottle is sealed under pressure, allowing it to maintain its pressure inside the bottle. Because it is difficult for a bubble of gas to form in a liquid, when you reduce pressure by opening the drink's container, the gas slowly bubbles out of the solution over an hour or so. Now, let's talk about the surface of one of the Mento mints. How would you describe it? Is it smooth or rough? Although it might look smooth, if you study it under a microscope, in fact it has large, rough bumps due to tiny bumps of sugar. You can feel this with your tongue, which is very sensitive to textures. When you drop the Mento mint into the Coke, the bumpy surface provides a place where bubbles can form. The rough surface traps microscopic bubbles of air, and carbon dioxide can easily flow into these pre-made bubbles, making them grow and rush to the surface of the liquid. This is called nucleation, and bubbles can nucleate other bubbles, causing a chain reaction. As lots of bubbles rush to the surface, they can carry liquid with them, and a narrowing of the bottleneck causes a jet to form. What will happen if we repeat this experiment, but at a higher temperature? The Coke shoots up even higher. This is because if we heat up the Coke, this will also cause the CO2 molecules to move much faster as they gain kinetic energy. As a result, the CO2 molecules diffuse out of the Coke much quicker, causing a higher jet. This is why, when fizzy drinks are bottled, it is done at low temperatures as well as high pressures to make it easier to dissolve the carbon dioxide. Temperature can also change the taste of your drink. If it's stored and served at a warmer temperature, a little bit more carbon dioxide will diffuse out of it, raising its pH and altering the taste a bit.
Thank you, Tabitha. Would anyone watching like to make a video with lots of different temperatures or different numbers of mints playing all alongside each other?
That would be a really good experiment, which would help find the best temperature for the Coke and Mentos demonstration.
If you do have a go, please keep the temperature of the Coke below 35 degrees Celsius to avoid potential burns.
Now we're going to hand over to Abby, Esme and Olivia, who are going to explore what happens when you mix together 2 different states to form a colloid.
Hi everyone, I'm Abby.
I'm Liv.
I'm Esme. Welcome to the DIY science section on making slime.
So the most important ingredients that you need are 45 millilitres of PVA glue, 3 millilitres of contact lens solution and 2 grams of baking soda. Some additional ingredients are a few drops of food colouring to make your slime colourful and some soap to give it a pleasant smell. About 4 millilitres will work. Around 2 millilitres of shaving foam can also be added to give it a fluffy texture. You'll also need a mixing bowl and a spatula.
Slime is made from polymers. A polymer is made up of very long chains of small molecules called monomers, which have bonded together. The PVA glue we use is a suspension of polymers. These are long chains of acetyldeoxyethene molecules, which have hydroxide groups on the chains. This will be important later. Polymers are like spaghetti, where the chains can slide past one another and keep the glue flowing. So the PVA is a very viscous liquid. The slime is made of lots of these long chains linked together, but there's a bit more to it than that, as we'll see after we make our first version of slime.
When making slime, parents must supervise younger children, as whilst the ingredients are usually safe, they must not be eaten.
First, pour 45 millilitres of PVA glue into your mixing bowl. After that, add 2 grams of baking soda into the glue and stir vigorously until it is mixed in really well. Add 3 millilitres of contact lens solution into the mixture and keep stirring until your slime gradually forms. If your slime is a bit liquidy, add more contact lens solution to it. It will make the slime more stiff. Be careful not to add the contact lens solution too quickly or your slime will become too firm.
2 liquids are combined to make slime: PVA glue, a viscous liquid, and borax in solution. Dissolving borax in water involves some complicated chemistry to do with buffer solutions. For our purposes, the important part is when you either have borax in water or boric acid, there will be tetraborate ions present. These ions, found in the contact lens solution, form weak hydrogen bonds with the hydroxide groups in the polymer chains linking together, which is known as cross-linking. This needs an alkaline environment, so the baking soda activates the process as it has a pH of 7.2.
The PVA glue no longer flows freely because the molecules in the slime have become weakly joined and the texture changes. The cross-linked polymer chains become too large to remain suspended and form the solid phase of a gel. Water is trapped by the chains, and so the slime is soft and flexible like other gels. The consistency of the slime is controlled by the ratio of glue to borax. If there is excess glue, the number of crosslinks formed is limited and you make a more fluid slime. If more borax solution is added, you make a stiffer slime because there are more crosslinks formed, so the chains have less freedom to move.
Shaving foam makes the slime fluffier because it contains air bubbles. Foam is a colloid. The dispersed phase is air and the continuous phase is a liquid. The new slime is a really complex colloid as you have a mixture of 2 colloids. The original gel and now the additional foam. To keep your slime stretchy and healthy, it is very important not to pull it fully apart, as that will break the crosslinks between polymer chains, permanently changing the slime's texture. Making crosslinks is very important in chemistry. Another example of where you will find them is in car tyres. Soft natural rubber is heated with sulfur and the resulting crosslinks make a strong, durable and less sticky substance.
Thank you. That's an especially fun one to have a go at yourselves. There are lots of variations you can try. Now it's over to India, who's going to show you how to make an unusual material called an oobleck. It's a non-Newtonian fluid that can behave both as a solid and a liquid.
Hi, I'm India, and today I'm going to be showing you how to make your very own oobleck. To make an oobleck, you'll need 2 components, cornstarch and water. For every 2 parts of water, you'll use 3 parts of cornstarch. For example, I use 250 grams of cornstarch and 167 millilitres of water. Then you just mix everything together and congrats! You'll have made your own oobleck. As you can see, if you jiggle the oobleck around with your hands, it behaves like a solid. However, if you stop subjecting it to force, it flows through as if it were a thick liquid. The reason this occurs is because of the very small starch grains suspended in oobleck. When more force is applied, there is more friction between the starch grains. This causes the grains to lock into an arrangement that resists deformation. The viscosity is thus increased, and as a result, the oobleck becomes thicker as it is stirred. However, when there is no force applied, it behaves just as a liquid would.
Thank you, and apologies in advance to parents for what might be about to happen to your nice tidy kitchens. Now we're going to have a look at what happens when all 3 everyday states of matter can exist together at the same time.
Hi everyone, I'm Lucia.
I'm Ankita.
And I'm Michelle.
In this talk, we are going to tell you about something really important in thermodynamics called a triple point.
At the triple point of a substance, you get the solid, liquid, and gaseous phases stable in the same container.
For water, this would mean ice melting as fast as it forms, water evaporating as fast as it condenses, and sublimation happening at the same rate as vapor deposition. And you would see all three phases until the system's temperature or pressure changes.
The triple point of a substance occurs at the temperature and pressure where all three of its common phases, solid, liquid and gas, coexist in thermodynamic equilibrium. For the purpose of this talk, thermodynamic equilibrium is when a system is in thermal equilibrium, where there is no net flow of energy within the system.
What do you mean, no net flow?
We can demonstrate what we mean about thermodynamic equilibrium using socks. Let's look at a glass of hot water with some ice cubes that have just been dropped in.
The system is not in thermodynamic equilibrium because thermal energy is flowing from the water to the ice. The water gets colder and the ice melts. If the system were in thermal equilibrium, water and ice would coexist. Any melting would be balanced out by some other water freezing, and so on. You can never truly isolate a system from its surroundings, and if the system and its surroundings aren't at the same temperature, then it won't truly be in thermal equilibrium.
The triple point occurs at a fixed temperature and pressure for every substance. This means we can use it to identify different substances. For example, the triple point of water occurs at 273.16 Kelvin, or 0.1 degrees Celsius, and 611.5 Pascal.
Because the triple point of water is one of its physical properties, it is used to define the Kelvin scale of temperature, and it is a standard fixed point temperature for the calibration of thermometers.
The triple point of water represents the minimum pressure at which liquid water can exist. At pressures below the triple point, such as those found in space or on the moon, solid ice changes state into water vapor when heated at a constant pressure. This is called sublimation, and we can show it using this pressure-temperature diagram.
We can show you a triple point occurring using our good old friend liquid nitrogen. Liquid nitrogen has a triple point of minus 210 degrees Celsius and 13 kilopascals. This is rather convenient as that temperature is only 14 degrees below the boiling point of liquid nitrogen in a lab and at 12% of atmospheric pressure. So you can use a standard vacuum pump to evacuate enough air to reach that pressure.
A cup of liquid nitrogen is placed in the vacuum chamber and the pump is turned on.
Please don't do this unless you know what you're doing. The tube leading to the pump was modified to include both cold and moisture traps. The pressure falls quickly at first. As we approached the desired pressure, the rate at which it dropped fell. Lowering the pressure makes the nitrogen boil more vigorously, and we were reaching the limits of the vacuum pump's performance. As the nitrogen boils, the faster moving or hotter particles leave the liquid first. This cools the remaining liquid nitrogen.
Over about 10 minutes, the temperature and pressure drops until a crust of nitrogen ice forms on the liquid's surface. If you look carefully, you can see boiling below.
By reducing the pressure, we had reduced the temperature of the liquid nitrogen and followed the temperature-pressure curve down until we reached nitrogen's triple point. Gas was still being produced, and the system cycled between melting and freezing.
Thank you, that was really cool. Now we're going to hand back to Tabitha, who is going to be showing you how to make a drink which will work even better if we are able to store lots of it at water's triple point.
Hi, I'm Tabitha, and I'm going to show you how to make a really easy and delicious slushy at home. You will need the following ingredients: about 12 large ice cubes, 1 tablespoon of table salt, 1 cup of fruit juice or fizzy drink. You will also need 2 Ziploc bags or similar, 1 big and 1 small. First, fill the large Ziploc bag with ice cubes and salt. Then fill the smaller Ziploc bag with your drink of choice. I'm using Fanta. Put the bag with your drink inside the bag with the ice and make sure they are completely shut. Shake it for about 5 minutes. I used oven gloves to hold it because it's really cold. When you see it turn to ice, pour your slushy into a glass and enjoy. Salt is the key to lowering the temperature of the drink. When salt is mixed with ice, it lowers the freezing point of the water. This is called freezing point depression. The ice leaves your freezer at a temperature of around -18 degrees Celsius, and it starts to melt when it warms up to its freezing point. With table salt, or sodium chloride, you can depress the freezing point of water below -20 degrees if you use enough salt. This would be a bit too cold. Using 20 grams of salt with 180 grams of ice will result in a 20% salt solution eventually, which has a freezing point of -6 degrees Celsius, although the solution will be a bit warmer by the time all the ice is melted. I hope you have lots of fun making slushies this summer.
Nice one, Tabitha. I'm off to try that out once the talk is over, just before I rewatch our WOMAD colloids talk. And now we're moving on to looking at particle accelerators and how they can help us create unusual states of matter. This section uses lots of footage from CERN's archives with their permission.
Hi everyone, I'm Monet.
I'm Safari.
And I'm Lucia.
In this talk, we are going to tell you about some really exciting technology, particles accelerators.
A particle accelerator is a machine that accelerates charged particles, like electrons and protons, to extremely high speeds, close to the speed of light. Electric fields accelerate the particles, and magnetic fields are used to steer them and focus them into tight beams. The beams travel around an accelerator in a vacuum, so the charged particles aren't obstructed by air, dust, etc.
Steering the beams allow you to make them cross when and where you want them to, so that the beams of charged particles traveling in opposite directions can be made to collide. Smaller particles accelerators are used in a wide variety of applications, such as proton beam therapy for cancer treatments, radioisotope production for medical diagnostics, ion implanters for the manufacture of semiconductors, and accelerator mass spectrometers for identifying and studying chemicals.
Technically, even an X-ray is a particle accelerator. It accelerates electrons up to very high speeds and smacks them into tungsten targets. As they slow rapidly, the electrons radiate their kinetic energy away as X-rays.
An early breakthrough in studying high-energy particles was made by Cecil Frank Powell at Bristol University. He used balloons to carry photographic plates to extremely high altitudes to detect and study high-energy particles.
This led to the discovery of subatomic particle called the pion, which he won the Nobel Prize for Physics in 1950. The advancement in the study of high-energy particles like the pion led to the development of particles accelerators.
There are two types of particle accelerators: linear accelerators called LINIAC and circular accelerators called cyclotron. Linear accelerators accelerate particles for a set distance to a set energy without having to deflect them, whereas cyclotrons allow particles to go round and round until they gain their desired energies, all the while being accelerated to higher energies by a strong electric field. The particles need to be deflected by a strong magnetic field so that they can loop around and collide.
One of the best examples of a particle accelerator is CERN's Large Hadron Collider, or LHC, which is the world's largest and most powerful particle accelerator, having a circumference of 27 kilometers and reaching energies of up to 13 tera-electron volts.
It uses over 1,000 superconducting magnets, with each magnet being 15 meters long and weighing 35 tons. The magnets reach magnetic fields of 8.5 Tesla, way larger than the Earth's magnetic field.
The invention of particle accelerators has led to the discovery of new particles, such as the Higgs boson and the top quark. Beams of charged particles are made to cross in large particle accelerators, such as those used in the LHC's ALICE and ATLAS experiments. By studying what happens in these high-energy collisions, we can study the fundamental building blocks of our universe.
To make magnetic fields strong enough to bend the beams of particles in the LHC, you need extremely strong electromagnets. CERN quotes a current of 12,000 amps, which means you need to use superconducting wires to avoid vaporizing your conductors, or at least wasting huge amount of energy as heat, which would be very difficult to get rid of. You can see some examples of exotic state of matter when the LHC is running. For example, CERN were the first to observe a quark gluon plasma in the year 2000. This only occurs at energies way higher than found in regular plasmas or even stars.
A little bit later, we're going to explore some fun things you could do with superconductors.
Thank you for bringing us up to speed on such a high energy subject. For our last Science at Home practical, Monet and Christy will be showing you how you can experiment with electric fields in your living room.
Hello, I'm Monet.
Hello, I'm Christy. Welcome to our Science at Home section on electric fields. There are two types of electrical charges, positive and negative. Opposite charges attract while like charges repel. An electric field is a charge that experiences an attractive or repulsive force, usually around a charged object. Objects in our daily life are normally uncharged, or if you prefer, neutral. This is because they contain the same number of positive and negative charges, and therefore there is no net charge. To make an object have an electric field, you can separate the positive and negative charges on the surface of the object, like this balloon we have over here.
If you rub a balloon on your hair, or better still, a nylon jumper, electrons are transferred from the material onto the balloon. We have created static charge. Part of the surface of the balloon is now negative, and the charge can't travel anywhere or spread out because the balloon is made from rubber, which is an insulator. We can easily show there are two types of charge. Charge to balloon, and they will repel each other, while either one of them will be attracted to the material, or my hair used to charge them. If you make the charge big enough, eventually a spark will jump through the air, making a plasma. When you pull a jumper over your head quickly, the little crackles you hear are sparks created in the same way. Do it in the dark, and you might even see little flashes of light as electrons and ions from the plasma in the spark recombine.
It is always the electrons that move when we create a static charge. The balloon has a negative charge because it has gained electrons, while the material will have a positive charge because it has lost electrons. As the balloon is now charged, it has an electric field around it. This device over here is used to detect electric field. It's made out of a ruler and a crisp packet paper taped onto it. And the crisp packet paper is used because it is a conductor. Material from an insulation blanket can easily be used in place of the crisp packet paper because it is very flexible. When you bring the balloon close to the crisp packet paper, the electron from the tip of the crisp packet paper is repelled away, and this is because it is a conductor, and electrons move freely in the crisp packet paper, and the tip becomes positive, which is attracted to the negative surface of the balloon. And now you have created an electric field detector.
If you get enough charge on your balloon, you can make your hair move too. Each hair becomes charged, so they are attracted to the balloon, but repel from each other, giving you an especially bad hair day. When you bring your charged balloon close to a wall, the balloon is negative and the wall is neutral. While the molecules in the wall are fixed in place, the electrons in the molecules get redistributed a bit to leave the sides of the molecule facing the balloon with a slight positive charge.
Opposite charges attract, so the balloon will be stuck onto the wall. It stays there for a while at least because they are both insulators and charge cannot dissipate. However, it will gradually leak away over time.
You can do the same trick with many insulators. Here, our balloon is being used to pick up cat litter. Even if Piggy, my cat, isn't very impressed. You can do it with paper from a hole punch and all sorts of things. Watch what happens if you bring a balloon near running water. The stream bends because the water is a polar molecule. The hydrogen ends are a bit positive and the oxygen in the middle is a bit negative. The molecule is neutral, but it has oppositely charged regions. As you bring the balloon near water, the molecules orient themselves so that the positive bits face the negative charged balloons. You see the bending only happens near the balloon.
In a particle accelerator, electric field is used to accelerate charged particles. In physics, however, it is quite complicated as it involves turning on and off an electric field at the right time in a cyclotron. But we can use an analogy. If we bring a balloon close to an uncharged can, the electrons will be repelled away on the side that is closest to the balloon, and this will make the can slightly positive, attracted to the balloon. If you move the balloon, the can will follow, and you actually use changing electric field to have accelerated a rather large particle.
Well, that was a highly charged practical. We're going to finish this session with Julia, Amelia, and Amisha, who are going to explore the super cool physics of superconductors.
Hi, I'm Julia.
I'm Amelia.
And I'm Nimesha.
Superconductors are truly amazing materials. They're able to sustain currents with no loss of energy, making them vital in applications where large magnetic fields are needed. For example, the electromagnets used to steer beams of protons in CERN's Large Hadron Collider use superconductors to help generate the huge magnetic fields needed to bend the paths of these particles, which are traveling at close to the speed of light.
The first superconductor was discovered just over 100 years ago, in 1911. It took us until the late 1950s to explain how the first family of superconductors work, and physicists only found the first high-temperature superconductor in 1987. However, even high-temperature superconductors need extremely cold temperatures to work. The phrase high temperature turns out to be relative. Luckily, we can reach a high-temperature superconductor's critical temperature with liquid nitrogen, which boils at minus 196 degrees Celsius.
Because of their ability to conduct currents without losing energy, superconductors show some unusual behaviour that can seem almost like magic until the physics behind them is explained.
While above its critical temperature, magnetic fields will pass through a material which can superconduct. However, a material that has become a superconductor is not allowed to have a magnetic field inside it, so when the material drops through its critical temperature, it expels any magnetic field passing through it. If you cool a superconductor with a magnet on top of it as it passes below its critical temperature, the opposing field from currents generated on its surface repel the magnet, pushing it off. This is called the Meissner effect.
Yttrium barium copper oxide, or YbCO, as its full name is a bit of a mouthful, has a critical temperature of minus 180 degrees Celsius, and the Meissner effect can be demonstrated by cooling it from room temperature to minus 180 degrees Celsius and below using liquid nitrogen. One way of explaining this expulsion is to imagine that the magnet is inducing a current on the surface of the superconductor as it starts to superconduct. This current has a magnetic field, which opposes the external field, stopping the field from entering the material. A superconductor can be described as a superdiamagnet.
The diamagnetic material becomes magnetized by an external magnetic field in such a way that the field of the diamagnetic material opposes the field of the magnetizing material, and the two materials are repelled. Normally, this behavior is so weak that it is not easily observed. However, the large currents induced in superconductors due to their complete lack of resistance means that the effect is very strong in them. You can get a magnet to apparently levitate above a superconductor if you position it very carefully. But because this is diamagnetic repulsion, it is very unstable, and even a slight disturbance will cause the magnet to fall off.
When you drop a magnet through a metal tube, as its field changes across the surface of the tube, a current is induced. Lenz's law says that this current must have its own magnetic field which opposes the motion. This is a consequence of the conservation of energy. Kinetic energy from the falling magnet is transferred into electrical energy, so there must be a force that causes the magnet to slow down. As the magnet falls, you reach a complicated equilibrium.
Resistance causes the current to die away, so the magnet must move continually to replenish it. If the magnet moved faster, there would be more current induced, producing a larger magnetic field, so the magnet would slow down. However, if the magnet slowed, this would produce less current. Less current means less magnetic field, allowing the magnet to speed up again. So the magnet must fall at a constant rate. But what happens if there's no resistance?
Here we have a tube made from bismuth, strontium, calcium, copper oxide, BSCCO for short. Below minus 165 degrees Celsius, it is a superconductor. If you drop the magnet into the tube, it remains suspended at the mouth of the tube. As the magnet approached the tube, it induced an electrical current, just as with the copper tube.
But the superconductor has no resistance. Therefore, the current does not die away, and the magnet will sit suspended until either it's pushed or the tube is allowed to warm above its critical temperature.
A type 1 superconductor can never have a magnetic field pass through it. All high-temperature superconductors are actually type 2 superconductors. However, not all type 2 superconductors are high-temperature superconductors. Type 2 superconductors have an extra strange property.
Unlike type 1 superconductors, a very strong magnetic field can penetrate through them in small regions where the material's ability to be a superconductor breaks down. The region behaves like a tube, carrying the magnetic field through the non-superconducting region, so they are called flux tubes. These non-superconducting flux tubes are surrounded by electrical currents, which trap the magnetic field, and the value of the field inside the tube is not allowed to change.
If you have a very thin sample of a superconductor, this can have an interesting effect, because defects in the structure of the material will trap or pin the non-superconducting tubes in place. This means if you cool a type 2 superconductor in a magnetic field, then it gets locked in place. It can't move left or right or up or down.
Here we have a YbCO sample encased in plastic and with foam to store liquid nitrogen. The sample is about 1/10 of a human hair thick. If we have magnets that alternate between north and south poles facing up, we find that the superconductor gets trapped in place as it superconducts. We can't easily push the superconductor, as this would induce a large current with a magnetic field that tries very hard to stop the superconductor from moving. And it looks like it's levitating. Is it actually levitating though?
It's really not levitating at all. The magnetic field is trapped inside the superconductor and resists changes. It's only happy when the field remains the same. You could think of it as if, when the right way up, any attempt by the superconductor to fall down induces a current that pushes it back up. When held upside down, any attempt to fall away from the magnet induces a current with a magnetic field that stops it from falling away.
If we move the superconductor onto some ring magnets, you can see that it will spin freely. This is because the field around the ring is the same, so the superconductor is locked to the circular shape of the resulting field. And if you place the superconductor on a track, the curving magnets will actually steer it as it zips around, smoking merrily.
Of course, you can simply define a state of matter as something with a distinct set of physical properties. When those properties change, you have a change of state.
It's kind of fun to realize that in order to observe new states of matter in a particle accelerator, we need a state change in its wires to happen first. As we saw, the superconducting state is vital to the operation of these electromagnets.
Huge thanks go out to the Northern Ireland Science Festival for inviting us to present today, especially Sarah Jones in Belfast and Rachel McDermott in Derry, Londonderry, along with the team at Nerve Centre.
Thank you for listening.